folks. Today we're going to be doing section 9.5, which, as you can see, is solving trig equations. Kind of started with this last time. Section 9.1 was simplifying and verifying, but naturally, equations being what they are, you have to employ simplifying at some point. Anyhow, there isn't really a packet for today. I'm going to refer to two older packets. Firstly, you had this from last time, as I suggested, sort of chop it up this way. The identities will be useful, potentially, right? But not as much today. A couple of the examples that I had noticed in our textbook, they had referred to the sum and difference identities and the double angle formula. You are not really responsible for those yet because, at least according to the schedule, here is the schedule, that material, sum of difference formulas or sum of difference identities are 9.2, the double angle formula and the half angle formula are section 9.3, and then there's something called product to sum to product identities. Those are next Thursday, right? Which is later this week. All right, so we are here December 8th, when we're doing just section 9.5. Now, obviously, because of the numbering, this would normally come after these three sections, but for whatever reason, whoever made the master syllabus decided to do that first. So, in keeping with that, I'm going to try to exclude those things, whatever necessary, and it wasn't that important. Not yet, anyhow. I would, if you have this, again, this sheet from last time, where we're accumulating or compiling a list of identities, chop it up this way. This material would have been from 9.1. Okay, and note that these are even identities and these are odd identities, which are helpful if you have a negative input, how to decide how you could rewrite that. All right. This would be 9.2 and 9.3, so you really don't have to worry about it right now. In addition to that, because we're solving equations, the older techniques are still useful. So like the algebraic techniques, even though these are, transcendental based, the quadratic equations, those techniques involved would still potentially be useful. You would just have to make a sort of adjustments, more or less disguise whatever you're given to look as though it were algebraic, and then go about this process. Factoring in the zero product rule in particular are useful, as are square root property and maybe quadratic formula. Right? So this is from a while back. I'm going to have this in announcements so that you could use it as a reference if you happen to have lost it. Okay? So we'll keep that. Now, as I am inclined to do, let me give you an overview. Take a sip here. My coffee and my water, like a bird with that caffeine addiction. All right, let's see. Let me just make a little room here too. Oh, the nice mark is going to be stubborn today, I can see. Let me turn the light on too. There we go. Let's discuss solving techniques that we are familiar with. That's one of the nice things about math. The foundational information gets revisited, all right, and is always useful. This is my older sister, I believe. I'm sorry. My phone was really stupid today. Deep here. Let's build an overview of solving techniques, not as in-depthly as I would like, just for the lack of real estate here. But we have some techniques that we will borrow from polynomial-based equations. Those will still be useful. All right. And this is kind of the history of, when we are taught these things. This is the usual order. Right. The first type of equation that you're taught to solve is basically a linear equation, or a degree 1. And essentially you're taught to do two things. First and foremost, right, in order to solve, you perform opposite operations. Whatever you do to one side of an equals, you do to the other. Right. There is also simplifying that has to occur, and that would really be the first preliminary step. Right? When you simplify each side independently first. Right. Right, how so? Well, you add or subtract like terms. That writes really nice. And you may also end up having to distribute. This is really sort of the preliminary step to simplify each side independently first. All right, but this is more than often than not what you do. All right. All right. Opposite operations. Then immediately after that, we begin with quadratic equations. Which is degree 2. And the slew of techniques are those, as I mentioned previously, that would be found in this sheet. Right? It is again primarily, first and foremost, factoring and the zero product rule in tandem. And then if failing that, because not everything can be factored, usually the quadratic formula or perhaps one of these other two options. The completing the square step is useful, but not always necessary. Usually people, because it's kind of involved, they will opt for the quadratic formula instead. My sister has to go to the doctor. Anyhow, just sort of to organize this. If opposite operations is the essential technique for solving basic linear degree 1 equations, that will still be incorporated into anything more complicated ultimately. But the real go-to technique for quadratic equations is factoring. So I'm going to try to sort of abbreviate that by writing the word factoring as a factor. So you see it like that. And zero product rule. That means you set something equal to zero. Right. There are other techniques you could square. You could do square root. Right. You could complete the square. Right. And of course, the quadratic formula, which, as I'm fond of saying, is like swatting a fly with a bazooka. It isn't always necessary. Sometimes it's serious overkill. I wouldn't swat flies in general. I would try to let them out. But that's the analogy, right? The quadratic formula. Geez, I think this is a dud, so perhaps I should not use that word. Anyway. I'll try to confine myself. Then there are rational equations, which are technically a polynomial on top of a polynomial, but let's identify them as something independently. Rational equations. How does one deal with those? Well, hopefully my green will cooperate. Usually what you end up doing is write an equivalent equation, and in this process it could be with a common denominator, or it could be eliminating the denominator entirely, which is usually what you're encouraged to do. So you would write an equivalent equation using the lowest common denominator. Right. This basically eliminates, you don't have to do it this way, but it eliminates denominators. Of course, when you do that, the caveat is that from extensive manipulation, especially if you're multiplying or dividing by a variable, which is unusual, all right, you may create an extraneous solution, or rather an equivalent equation that produces extraneous solutions. So you have to look for those, duds, if you will. You have to be mindful of that as the all-seeing eye. Okay. Then, just sort of to group them together, there are exponential and logarithmic equations. And they have quite a lot of options, right? Remember, these are inverses of each other. And usually what you try to do is maybe apply the inverse. There'll be something of a cancellation effect. Or to translate into the same bases, in which case you will have something that is referred to as one-to-one. That would be very useful even now. And then there's the subject of U substitution. That's also very useful. U substitution is basically disguising whatever you are given so that it looks like an algebraic equation. You take something ugly and complicated and you just include the essential. All right? You don't get bogged down with the fine details while you're going through the process of simplifying. Right. This is a very useful technique, as is one-to-one. All right. Now, the trig equations essentially, that is the new material that died officially. Okay. The trig equations, let me just re-highlight that. Ooh, that is much nicer. We're going to try to employ algebraic techniques. Right. And if failing that, maybe use identities. All right. To simplify. Remember, to refer back to this, this is kind of the preliminary step, right, in any situation, step 0, if you will, to simplify each side of an equals independently, right, and then go for, you know, the usual shtick, you know, the usual process, right. Being that we are dealing with trig equations and we have compiled some identities, right, we might be able to use identities for that purpose, for simplifying first, right? Right. And then we could maybe go about this process, borrowing something from earlier, all right? Factoring comes up a lot. U substitution comes up a lot. I would say even translating something into the same basis is kind of like that. It maybe is not accurate to call it basis exactly, but a function that has an argument, all right? Would like ideally to match on two sides of an equal sign. Okay. Okay. Now I must erase this, unfortunately. Pardon me a moment. Some of this is getting erased and some of it's not. There it goes. Evidence. The nicest markers somehow are the most lingering. And that is not a permanent marker, I assure you. Tell if it's because of the temperature, which it may be. There's a relationship there between the tenacity of the color and the temperature in this room. But it doesn't do it to all of them at the same time, just certain colors. All right. Now, a couple of things to bear in mind, right? Things to remember when solving trig equations. I don't know if that's visible. Put that in there. All right. Things that are like algebraic equations. Only specific values may be solutions. You know, if you've ever done anything quadratic, and you know that after having used the quadratic formula that you ended up with you know, an imaginary number, you go, all right, well, I can't use that, right? Or if you were doing something that applies to a real life physical situation, something that, like, you know, that involves a measurement in geometry, like a length or an area or something. You know that if you get a negative number, there's no such thing as a negative physical dimension, right, in geometry. So you would rule that out, right? That's something that you have to kind of be conscientious of when you're solving trigonometric equations too, right? The domain restrictions come into play. So only specific values, even though they may be mathematically possible, would you actually keep. Let's get all done. Let me get another marker here. Package again. They go really quick. Blue. Okay. Let's see. Sometimes we're asked to find solutions over a specific interval. Very much like inequalities, right? Other times you're asked you're looking for all possible solutions. Let's see. Now, thing to bear in mind, trig equations, that's very faint for Brendan Walker. Trig equations are periodic, right? So in theory they have you know, infinite y values that are the same. Let me just include this too. You know what the truth is? I should have put this here, sorry. Trying to organize here. Let's just move this thought over here. The reason why you want to look at a specific interval is because periodic functions are in fact infinite. Like rational equations, you know, domain has to be considered. Let me just make sure this is in the frame and also visible. It's a little faint. Okay. Let me highlight a little bit here. Rational equations, all right, are equations that, remember, look like this, where there's a variable in a denominator. And you know that it could be more complicated than just simply x, but for argument's sake, for the sake of simplicity, what is the one number in the world you're not allowed to have as a denominator? Can't be equal to 0, right? Which limits the domain. It could be, in theory, for this example here, this is part of an equation. X could be anything, but it can't be that one thing. All right? Everything except that would be a better way of saying it. So the domain has to be considered, you know? Well, that's why they use this phrase, all possible solutions. All right? And this is why we use this phrase. If you're looking for solutions over a specific interval, it's because periodic functions are infinite, right? So these two things would be useful to keep into your mind. Right? As a side note, probably should have swung that over more, but I didn't think to do that. Remember the period the time it takes to complete one cycle of a wave, right, for sine and cosine is 2 pi, right, under normal conditions, right? That means that the y values repeat. Every 2 pi. This will be useful too. Right. The sine of theta, right, once you have figured out what that value is, you'll get the same value, right, in multiples of 2 pi. This is just an integer, k. All right, I think we can get started in terms of actual examples now. Trying to point out the pitfalls first. Good game. Okay. Okay. There's quite a lot of these, so let's establish sort of a pattern here. Blue may give me trouble, but it writes well. Let us start with finding all possible exact solutions for this trig equation. And the frame is a little faint. It's a brain markup. For this trig function, cosine of theta. Maybe this is my temperature theory at play here. It looks like it has a lot of flair. Okay. Cosine equals 1/2. I hate to write in red because red really emphasizes things, so I reserve it for that purpose. But I may have to. Green doesn't really work very well. So, cosine of theta, the angle, equals this ratio, right? When you do these, all right, get in the habit of drawing a simple picture. Draw a unit circle. All right, almost every single time. All right, it will help you establish a couple of things. All right. And remember trig ratios. All right. Trig ratios from the perspective of SOHCAHTOA. All right. Cosine is adjacent over hypotenuse, and from the perspective of standard position, in which case you would replace adjacent and hypotenuse with an X and an R usually. So down here I'll write it. Cosine of theta is SOHCAHTOA adjacent over hypotenuse, which 9 times out of 10 means X over R. Okay. If you have the ratio of 1/2, right? You have an X value and you have an R value. All right. So, and as another rule here, only X's or Y's can be negative. All right? R is always positive. That sounds like a yak out there. Maybe the door's left open. So here is a unit circle. Terrible unit circle, but you get the idea. It's kind of amoeba shaped the way I drew it. You have to ask yourself where is, since this is a positive 1, where is X positive, right, in the unit circle, right? In theory, X could be positive in quadrant 1 or quadrant 4. So basically in this region and in this region. The advantage to taking the time to consider that every time you do one of these problems is that you're basically eliminating this half of your situation. All right. So start out with a diagonal line. It may not end up that way, but draw a diagonal line here and here, connecting to the edge of the circle. All right. And then just draw a triangle in it here and here. Right? You would indeed have a positive X here from this point to this point. Okay. Now, if the X value is positive 1, remember in your special right triangle relationships, you have basically two choices. You have the 30, 60, 90 special right triangle, and you have the 45, 45, 90. And you could kind of guess which situation you're going to be simulating here. By looking at the dimensions that you're given. So in the case of the 30, 60, 90, if this is the 30-degree angle here, then the square root of 3 runs that way. All right? And that would make this 1 and that 2. Sometimes, and it might be in this case as well, the 30 is moved. Okay? So we would have to just change the orientation of these dimensions. Just to complete this thought, if you had the 45, 45, there's a little less thinking involved because there are two similar angles here. Well, they are equal, I should say. These would be the relationships. 1, 1, square root of 2. Right? So very likely, if you see these dimensions 1 and 2, you're probably dealing with this situation. It just may be oriented differently. Now, if we're saying that there's an angle here, and that's how we normally read angles in standard position. The initial side being on the horizontal axis and the terminal side up from that. I'm going to read this from the perspective of SOHCAHTOA again. Adjacent to this angle would be positive 1 in that situation. And then the radius would be 2 here, otherwise known as the hypotenuse. You have to toggle kind of a lot, back and forth between standard position labeling and SOHCAHTOA labeling. It would be useful in this case to do SOHCAHTOA. Why? Because if the square root of 3 dimension is running along the side of the triangle that is between the 30 and the 90, and the 1 is running along the side that is the 60 and the 90, that implies what this angle actually is. This is 60 degrees, all right? Because it's really that side. It's just oriented at a 90-degree angle. Okay. Why bother with all this? Well, because we have now established how far from 0 to here we have 60-degree angle. All right. What is that in pi radians, which for whatever reason the book seems to have that preference? Don't forget how to translate. You may have a reference somewhere, and I won't begrudge anybody that, but remember to convert. If you have 60 degrees and you want to convert to pi radians, use the conversion factor pi over 180 degrees. Right? And then treat it as if they were fractions. Cross simplify, cross out zeros, that's as if you divided each by 10. This and 6 and 18 have a common factor of 6 ideally as a GCF, so 6 divided by 1 is 1. And 18 divided by 6 is 3, which means that this is really pi over 3. So you could read this instead of as 60, you could read this as pi over 3. All right. Now, we're going to try to read this in the standard way, which is counterclockwise, weirdly, right? And therefore, we will go around the circle this way to figure out how many degrees that would be. All right. Realistically, when you're trying to figure out whatever 100 degrees this is, a couple 300 perhaps, you end up somewhat ironically having to read it backwards, at least at first. So this angle here would in theory have to be the same angle here, right? Because of the dimension 1 and the radius of 2 being the same, all right? So it would just be negative 60 in theory. In order to figure out what that dimension would be, you're really doing this. You're going, well, the whole way around is 360 minus an additional 60, which is exactly 300 degrees. But it's 300 degrees if you read it from this direction versus reading it from this direction, which is arguably easier. Again, I would never get mad at somebody for saying, oh, it's negative pi over 3. That's true. But try to read it in the normal orientation. All right? So we're going to calculate what this is in pi radians instead. If you have figured that this is 300 degrees and you want to convert it to pi radians, all right, pull the same tricks. Knock off a 0 here, knock off a 0 here. These are both divisible by 6 again. 30 divided by 6 is 5, 18 divided by 6 is 3. That means that this is 5 pi over 3. Again, reading all the way around to this terminal side, all right, we have 5 pi over 3, right? Those are all possible exact solutions for this. The reason that I specify exactitude here is because we took dimensions from a special right triangle. Anything that is not from a special right triangle, you're probably going to have to round a decimal at some point. So it's not really exact. All right. Anyhow, these pi over 3 and 5 pi over 3, those are your solutions that are feasible. All right. Moving on. May have to spray this in a little while. Just so my markers get a bit more agreeable here. Okay, let's do something that is more algebraic. We're going to end up having to draw a picture once again, but it's going to be cool. Reluctantly, I will use green. Example 2. I hope that's visible. All right. In this instance, you would solve the equation in the exact interval. All right, so let's say hypothetically you had this equation, 2 cosine of theta minus 3 equals 5. And the exact interval that they want you to give get solutions, it's -5, it's supposed to be. Is from here to here. 0 to 2 pi. Right. What does that mean? This is sort of an inequality way of writing it, right? Versus, you know, the shorter notation, which would be something like this. All right. I guess this is kind of a little bit more intuitive, right? Because you can see that the angle is somehow in between 0 and 2 pi, all right? If you feel more comfortable furthermore, all right, throw in degrees and remember that this is really 180, right? All right. Now, it could be exactly equal to 0, but it has to be not quite including one complete rotation because you'd be in the same place anyway. All right. So we don't want to go past 2 pi. In other words, one revolution around the circle and that's it. Is the confined place to work. All right. I'm just going to keep those like that. All right. Now, insofar as the process is concerned, all right, you're going to treat this algebraically, all right? Algebraically, what do we always try to do? We try to isolate something. In this case, we're going to try to isolate the trig function and then try to isolate the variable in question, theta. If we're trying to solve for the angle, right, we got to get that is an argument of a function, right? Quasi function. And so we have this step of moving stuff around first, right? So let's do that. All right. If you're going to isolate this, then you're going to move 3 from here to here first, right? The old technique's opposite operations. So you're going to add 3 here and add 3 here. This cancels, right? You're left with 2 cosine of theta is equal to 1 of each sign. You subtract really, so you get 2, and you take the sign of the larger magnitude, which is a negative in this case. So you have -2. Then move the coefficient of cosine, which is to divide by 2, and then divide by 2. Now this problem is going to be interesting because it's going to have a peculiar picture. What happens when you divide something by itself? You get 1. The only caveat is that technically it's a negative divided by a positive, so it's a -1 overall, right? Draw a picture at this point. Draw a unit circle. Right. To answer the question, where is, in this case, such and such. All right. This ratio, all right, would have to be technically -1 over +1, right? Because that would be a negative x, and this would have to be a positive r, because the r is always positive. So in this case, where is x negative? Here is a unit circle diagram. And I'm going to draw a circle in here. The locations of x being a negative are either the second quadrant or the third quadrant, technically, right? Now, start out by drawing what usually is the case, a diagonal line. You can end up having to modify the picture, but just to satiate that this is possible, quadrant 2 or quadrant 3, draw a diagonal line here and here. Now look at the dimensions again, x and r. If this is a unit circle, and it is, right? What is true about the radius, fundamentally? The radius is equal to 1, right? But it just so happens that the x dimension is exactly the same thing except that it has a sign. In this instance, the x and the r are the same dimension. So you're not dealing with a diagonal line in this situation. You're dealing, in fact, with a line that is running along the axis from here to here. X equals 1, just in the negative direction. Now, you don't need a calculator to answer the question of what the angle is then. All right? It is actually not in quadrant 2 or quadrant 3, or you could say that it is in both simultaneously or neither. It is on the axis, strictly on the axis. So if this is 0 degrees and this is 90 degrees, what is this dimension here? 180 degrees, right? What is that using the pi symbol instead? 0 degrees is just 0 always. 90 is pi over 2. What is the alternative for saying 180 degrees using a pi symbol? Just pi. That means that the answer to what is theta is that theta is equal to 180 degrees. It's just pi and nothing else. All right. Remember, we're confined to this interval, one full revolution. So within this interval, all right, there's just this one solution. If you wanted to get infinite solutions beyond the interval, all right, you would just keep adding 2 pi, you know. So another version of this from here to here is exactly 2 pi. Well, that is just pi. All right, another complete revolution would be from here to here. So you'd end up with 3 pi, and 5 pi, and 7 pi, and so forth. But in this interval, it's just this. Okay. I have to blow my nose because it's very cold. Excuse me. Do another of this type. This is an interesting problem for that reason I mentioned it is right on the axis rather than diagonal. Suppose you had to solve this. 2 sine squared of theta minus 1 equals 0. And again, in a specified interval, so from 0 to 2 pi again. Here. We're going to go through the process of isolating, all right? And let's see. All right, so I'm going to move 1 first from where it is over to the opposite side to try to get at least the trig function by itself. Granted, it is degree 2, but we'll deal with that. So add 1, add 1. And then you have 2 sine squared of theta is equal to 1. Divide by 2. And now you have this. You have sine squared of theta is equal to 1/2. Just like in quadratics, all right, if you have to, apply a square root, right, to get rid of a square because it is the opposite operation and there's a cancellation effect. Just realize this notation of having the exponent of 2 in the middle is alternatively written outside the thing entirely. So if you like writing it like that, that's cool, but if it makes more sense, put it here. All right? Just realize that it's not part of the angle itself. All right? This is the argument, just theta. Right? So for the sake of the cancellation, right, we will take a square root here, opposite operation, and whatever you do to one side, you're obligated to do to the other. All right? This will cancel this, and it leaves you with the sine of theta. Incidentally, I'm not switching from script to regular, just I'm insane. I can't help myself. When you're dealing with this, remember, if you take a square root, right, it's a positive or a negative in theory. Right? Kind of a thing I tend to have to remind myself after the fact. But the quotient rule for radicals says that if it is more convenient, you could break this up into two things. So you could make this the square root of 1 over the square root of 2, all right, and then deal with them separately. The benefit of doing that is that perhaps one of them will escape the radical. In the case here, the 1 would. So what's the square root of 1? Just 1. So we have plus or minus 1 over the square root of 2. All right? You could rationalize this, but I would hold off on that just for a moment. Rationalizing is changing the appearance of this so that there isn't a radical in the denominator. All right? What you're gonna, if you did that, eventually you'd have square root of 2 sitting on top of 2. In this form, all right, you have something that is slightly more honest, you know, because that's telling you what the in this case the y dimension may be, right, and that is what the radius would be, square root of 2. This refers to a special right triangle. Right, in which case, specifically the 45, 45, 90. And the dimensions would be 1, 1, and the square root of 2. Right. What is interesting about this problem is that we're working in the usual interval of 1 complete circle revolution. But because we have a square root, we have a lot of things to consider here. All right. So I'm going to draw a simple picture, and what you'll notice is that we're going to get not even just 2 answers, but potentially 4. This is why it is a good habit to, draw the picture, whether you end up using the circle or not. If, I'm running out of space here, I'll erase this just because I don't need it. If this ends up being the sine of theta, you know that the sine of theta is the opposite over the hypotenuse, which normally means y over r, right? If this is a positive, firstly, right, where is y positive? Y is positive above the x-axis. So that means that we would have to look in the normal situation in the first quadrant, but also potentially the second quadrant. And that means that if I draw a diagonal line, whether I end up using it or not, I'd have a situation here like this, or like this, what we usually start with. Simultaneously, it's not just positive, it is also potentially negative. All right, so we have to wonder, where is y negative? Well, that is the whole kit and caboodle then. Because where is y negative? Below the x-axis. Right? So that means down here in the third quadrant or the fourth. So I'm going to draw a diagonal line here and a diagonal line here. Now, just sort of to complete this drawing here, I'm going to draw a right triangle there, and a right triangle there, and a right triangle here, and a right triangle here. This is a lovely picture here. All right. We know nothing else about x, we just know that y could be either positive or negative, right? So in this situation, this is positive y, right? And this is negative y. This would be positive x, and this would be negative x. And this would be negative y, and this would be negative y. Now, if again we have these dimensions, 1 over the square root of 2, right, in relation to, let's just start with this theta being here, right, it would be the 45, 90 triangle, right, because it has a 1 and, you know, the quintessential features 1 and square root 2 in it. So, if this is from here to here, a 45-degree angle, and all of these others would have to be a 45-degree angle, and this would have to be a 45-degree angle, and this would have to be a 45-degree angle. That is a reference angle for each of those right triangles. What we need to get is the sort of regular orientation way of reading this, which is from 0 to this point. Instead of saying 45, we'll use pi radians. What is 45 degrees converted to pi radians? We use the conversion factor pi on top, 180 underneath it if we want to cancel degrees. So you may have a reference. You could certainly use your calculator. In 180 degrees, there are 4 45-degree angles. So this is the way that it would simplify. This is pi over 4 read in the usual direction, counterclockwise. If I read from 0 to this terminal side, all right, in order to get what the degree number would be 180 back 45, so minus 45, which is 135, right? What is 135 degrees times the conversion factor of 180? All right, 45, 45, 45, I want to say this is going to be 3 of those, all right? 45 times 3 is 15, is indeed 135. Good. Okay. So the way that this simplifies is 4 here again, and this is 3. This is 3 pi over 4. All right. Then so I'm going to circle this because it's getting messy. That's one solution. This is another solution in this interval. Now, what if we read all the way to here? All right. All right. That is 180 plus 45. All right. You can convert, well, let me do the arithmetic first. All right. This is 225, right? What is 225 degrees times the conversion factor of pi over 180? It would be 45, 45, 45, 45, and an extra one is 5. All right. This would be 5 pi over 4. All right. And then one more. If you read from 0 down this direction here to that terminal side, all right, to get the degree number, it would be 360, perhaps minus 45, which should be 315. Is that in the camera? There we go. you could say 1, 2, 3, 4, 5, 6, 7. This would be 7 pi over 4. Essentially, it means 7 times a 45-degree angle. Okay? So those are your solutions in the usual interval of 2 pi. Right? Theta 1 is pi over 4. Right? Theta 2 is 3/4 pi. Theta 3 is 5/4 pi. And the fourth one is 7/4 pi. Okay. Getting cold. Let's do a weird one. That's kind of the normal situation. If you could do this problem, you could do virtually any of them, you know, because it's looking out for a lot and it incorporates a lot. What if you get something like this? The cosecant of theta is equal to -2, and you're looking in the interval of 0 to 4 pi. Okay. And you're trying to find the angle, right? Right. This is an example, the first one really, where you would try to use an identity. Right. That would again be referring back to this sheet. So here are, if you look on the identities that we have established to the point of section 9.1 at least, right? They don't bother to differentiate these, but from this compiled list of fundamental identities, you see a reciprocal identity. Cosecant is famously the reciprocal of sine. Right? So, right, what you can do is rewrite the problem in that way. If you take a cosecant and write it using its reciprocal identity, right, then it is really 1 over the sine of theta instead. Still equal to -2. Now, as with algebraic equations, we don't like to solve for something that is in a denominator. So you will algebraically manipulate this so that the theta is back on the regular tier, all right? Not as a denominator, which would be, you know, a negative exponent in theory. So I'm going to manipulate this. What is the opposite of dividing? All right, multiplying, right? So if I multiply by sine of theta here, for the sake of cancellation, I'm obligated, of course, to do it here as well. There is this cancellation effect. And now I have this. I have 1 left behind on the left, literally. And I have -2 times the sine of theta back on the regular tier. Get rid of the coefficient to isolate. So you would divide by -2 here and here. And now you have this. Now I know that down at the bottom here, this came from -2, but I'm going to have to make an adjustment for the reason I mentioned earlier. All right? If this is an R value, and it will be, it can't be negative. All right? I'm going to write this in more or less the usual sort of orientation, where I like the function on the left side. It doesn't have to be that way, that's just idiosyncratic. So sine of theta is equal to this ratio, right? The ratio of 1/2, and I'm going to make sure that the negative is attached to the top, even though it came from the denominator here, right? So think about this from the perspective of standard position, right? Yes, the sine of theta is the opposite over the hypotenuse, but in the unit circle we would refer to this as a y, and this is an r, right? So this is a negative y, and this is an r, right? Because only the x's, the y's can be negative, right? Now I'm going to draw a picture, right, to answer the question, where is y negative? Right. There's two places below the horizontal axis. It's either in the third quadrant or the fourth quadrant. So here's the unit circle, and here is a negative y here, or potentially a negative y there. I love drawing my right triangles. Remember, when you draw a right triangle, it's always perpendicular to the x, right? No drawing it like that, okay? So negative y here, negative y here. Right. If these are the dimensions that are quoted to you, or what you've derived, that this is 2 for the radius, and the other dimension is 1, all right, then I'm going to put negative 1 here. And in place of this, I'm going to put negative 1 here. These dimensions should look familiar to you because they come from, again, special right triangles. Right? And in the usual orientation, right, it's the 30, 60, 90 that involves a 1, a 2, and a square root of 3. Right? If you have these two dimensions, this would have to be the third one. Right? If you're reading it in the normal way, there's really no normal way, but let's say that this is the 30. It is between the 30 and the 90, which I'm using the block to indicate, that you would have the square root of 3. All right? That means that this would have to be a 60. All right? So what you have here is a 30. And what you have here is a 30. Because the y is opposite of that. Right? Opposite of 30 is 1. So opposite of 30 here would have to be 1. It's kind of looking at it backwards. What's opposite of 1? 30 instead. Right? That is the degree reference angle, right? So we need to figure out what this will be in pi radians, and then take into consideration more than just one rotation. So both of these are a bit annoying because we're not even in the first quadrant here, right? The first one technically would be reading from here to this terminal side, right? And to get to that terminal side, it would be 180 plus an additional 30, right? Which would be what? 210, right? That's 210 degrees. Right? I need the space, so I'm going to erase this. (210 degrees times the conversion factor of pi over 180. This is made of the common factor of 30, all right? So you can divide by 30, all right? You could cross out the zeros too as a technique. This is divisible by 3, and therefore that is divisible by 3. 21 divided by 3 is 7, 18 divided by 3 is 6. This is 7 pi over 6, all right? So writing this in pi radians, instead of saying 210 or just a reference angle, it's 7 pi over 6, right, to start with. If you go this route, you're technically going negative 30, right? You still want the pi radian dimension angle here read in the counterclockwise orientation. All right. So negative 30, if we want to get to it, is 360 minus 30, right? Which is what? 330. All right. Once again, what is 330 times the conversion factor? Pull tricks. They're both divisible by 3. 33 divided by 3 is 11. 18 divided by 3 is 6 again. This is 11 pi over 6. So that is the other possibility, right? In the usual one rotation situation. So this is getting a little messy. I'm going to rewrite some stuff, but for reference, those are the two solutions we start with. Put this here, put this here. Let me clean up a little bit. All right. Now, remember, the usual period is, 0 to 2 pi. All right. This is exactly double that, right? This is basically, if this is a 4 pi, this is 2 revolutions. Right. So here are our solutions, right? Theta 1 is 7 pi over 6. And theta 2 is 11 pi over 6, right? But let us say that we did another revolution here. Right? Right. What is this plus an additional revolution? Plus 2 pi. And what is this as well? An additional 2 pi. Right. You do have to, you could do this with your calculator, there's no sin in that, but just realize that you're dealing with fractions. So if you're doing it by hand, you need a common denominator. How do you express the amount of 2 pi using 6 as a denominator? It would technically be 12 over 2, right? Pardon me, 12 over 6, all right? 2 pi using 6's as a denominator is the equivalent fraction, 12 over 6, because 12 divided by 6 is still 2. Add the tops, right? That means that pi 3 is 19 pi over 6, right? In this situation, more or less the same situation. Write it as the equivalent, 12 over 6, because that's the equivalent of 2 pi using 6's, all right? Add 11 and 12, all right? And you get this 23 pi over 6. Okay. These are your solutions, all right? 7 pi over 6, 19 pi over 6, 11 pi over 6, and 23 pi over 6. Sorry, I'm getting cold. All right. How are we on time? We're doing okay. Here's another weird problem. Right? Suppose you had to solve tangent of the argument theta minus pi over 2. Maybe more than one way to do this, but what occurred to me is to borrow techniques established from the logarithmic equations, exponential and logarithmic equations. This is equal to 1, and the interval is 0 to 2 pi. Let's look at this as two halves for a moment. We're involving tangent here. There's no identity that I'm going to incorporate here. All right. Remember, tangent, regular ordinary tangent of theta is equal to 1 at what angle? You may or may not remember from graphs, right? A while back, when this first came up, let me just point at it. I had you draw a tangent, right? And to get you a feel for it, I had given you this basic table, all right? If you inserted pi over 6, otherwise known as 30 degrees, right, into the tangent function, all right? It would spit out an unfortunate decimal, really. Right? But there are two examples where you get a regular ordinary number. Tangent of 0 is 0, right? Tangent of, at 0 you get, if you plug it in the argument, you get 0 as an outcome. The other one is pi over 4, right? Remember, tangent has a peculiar period, at least insofar in comparison to sine and cosine. It's not 2 pi, it's just 1 pi. Right? Anyhow, if you insert a 45-degree angle, otherwise known as pi over 4, in the argument, that's what you get, the one satisfying point on the graph. All right? Here's a picture. All right? Tangent at 45 degrees, all right, is... That's code, yeah. Sorry, it's upside down. I'm reading it upside down. Tangent at 45 degrees is 1. The other things are estimated, or rounded rather, because they're decimals. But that is right on the grid line at 1, right? So, good to know that. You could use your calculator, of course, certainly. All right? But you got a nice round number to work with. So, tangent is equal to 1 when the angle theta is equal to 45 degrees, otherwise known as pi over 4. Right? So, let us say that we rewrote this problem. We're going to substitute 1 with what 1 equals, all right? The tangent of theta, all right? This is a weird sort of backward substitution, but you'll see why I'm doing this in a moment. Meanwhile, what's over here still? The tangent of this argument, that writes much better now, pi over 2, right? Look at what you have, right, doing this sort of weird substitution. A sort of, I hate to downplay it, but a backward sort of substitution. Right. You have a 1-to-1 relationship when you have a one-to-one relationship, you may not remember, right? But when you have a one-to-one relationship, that is the function that is here on this side of equals, right, is identical to the function here, then you could write another equation that involves just the arguments. Essentially, when there's a one-to-one relationship, you can write an equation with just the arguments. That is the stuff that you see in parentheses. Theta minus pi over 2 and pi in this case. Right? And I'm going to substitute this for pi over 4, all right? Because that is the only thing that would make 1, right? Where am I borrowing this from? Right? From way back when we were dealing with exponential and logarithmic equations. I want to sort of point at it if I can. I had made here sort of an overview diagram at the time, which I'm proud of, so humor me for a moment, Lee. I think it's good. It could always be improved, right? But I'm trying to find it. My hands are so cold I can't really manipulate things too well. There it is, alright. Here we go. It was an old overview diagram I had made a while back. How to solve a strategy for how to solve exponential and logarithmic equations. Well, if you start with something exponential, if you can get the situation to be same bases, sometimes they start out that way, sometimes they don't, then you can employ one-to-one property, right? In the case of exponents, if they have the same bases, then you could just write an equation that involves just the exponents, right? When you have a logarithmic equation, right, that is the same log on the left side as on the right side. Either you could, maybe it started out that way, or maybe you got it to look like that. You could write an equation that just involves the arguments a and b, right, because it's one-to-one. In a situation like this, we're basically doing that, right? It's just that it's a trig function rather than a logarithmic function. So, taking advantage of the fact that we were given a nice number, not a crummy number, we got 1, all right? There is an angle that produces 1, it's 45. So if I have this sort of weird substitution, where I say, no, instead of saying regular ordinary 1, I'm going to say what it's equivalent to is tangent of pi over 4. Now I can write an equation that looks like this, just the arguments. Pi minus what was here, theta minus a half a pi, right, is equal to pi over 4. So I have basically fractions of pi that I have to manipulate. I need this space. So here we have it. Write this in green. If this is theta minus a half a pi, then this is equal to pi over 4, really. Just move half a pi, right, in the usual way. What is the opposite of subtracting? Adding is just a weird sort of fraction to use, right? So we have pi over 2, right? These cancel, and that gives you what theta is, at least to start with, right? If you could enter this as 1/4 and 1/2 in your calculator, and it will tell you 3/4. If you're not feeling comfortable and fuzzy about that, just remember you would have to upgrade these to a common denominator, in which case it would be 4 2/4 of pi versus 1/4 of pi, all right? And then you would add 1 and 2 and you would get 3/4 of pi. All right. Now, the second issue thrown at you, the second little wrench in the engine here, is they're asking you to figure out what would be the solutions for the angle, right, in this interval, right, which is not the usual interval. For tangent, right, the usual period is just what? Is just pi. So this is another situation where you have double that interval, right? This is 2 rotations, revolutions, if you will. Okay. All right. In this case, you're not going to add 2 pi, that is the sign of a cosine. When you're dealing with tangent, you're basically going to add pi. All right. All right, so to start with, here's our first theta, which is 3/4 pi. We calculated it algebraically. Theta number 2, that's theta number 1, is going to be an additional period, all right? So add pi, all right? Again, if you're going to do that, you need something that has the same denominator if you're doing it brute force, which is respectable even still, all right? That would be what, using 4 as a denominator? 8, right? No, that's not quite right. I'm sorry. It would be 4/4, right? 4/4 is just 1, right? This is using a convenient denominator to combine these. What is 4 plus 3, right? The other one is therefore 7 pi over 4. These are your 2 angles, right? This is incidentally 135 degrees, and this would be 315. Which is interesting because look, it's the same digits in a different arrangement. All right. All right. If you're given something that doesn't have warm fuzzy numbers like 1, or something that incorporates a special right triangle relationship, you would use your calculator. Right? The thing is that the calculator has limitations. It will give you an error message if you potentially use dimensions it doesn't like because they're outside the domain. But just to show you, if you had something like this, sine of theta is equal to 0.8, right? This is not, even if you wrote it in its fractionist form, which would be what, 8/10, which is the same thing as 4/5, all right? You're going to use a situation like this. You're going to use, this is not a special right triangle. Relationship. All right, you will use your calculator, right? Remember, we use inverse trig functions to calculate an angle. My bread is dying now. Put that there. So the inverse sign, this is just this notation of that ratio, which is just written in decimal form. will tell you what theta is. So just to show you, illustrate here. Just be leery of the fact that you may have to change the mode a lot. All right. I personally, I don't want to corrupt you, but I like degrees. All right, just because I'm familiar with it. All right. So you could have it set to just regular decimal radians, which is a little less familiar to me personally. All right, but I'm going to start with degrees, and then I could always convert to whatever. So if you want to get the angle here for the sine, what the angle would be if this is the ratio. Use the inverse function to produce the angle. So you have to hit second, and then in this case it's sine. And you'll see that you have the notation of quasi-exponent of -1. It's just a notation. And then put 0.8, right? And it will tell you the angle of, what is it, about 53 degrees, right? Notice that it is an infinitely stretching decimal, though. So you're going to get an approximate, right? Theta in a situation like this is about equal to 53 degrees. The textbook that we are using seems to have a preference to have things not even in pi radians, which to me would be the logical equivalent, but in just full-blown radians, which is a decimal. If you did the same thing, and I'm going to go back and change the mode, just beware, all right, that if you had this in regular radians, it's not pi radians, it's just regular radians. So I'm going to duplicate what is written here just by highlighting it. And there it shows up again underneath it. And notice what the decimal equivalent would be, 0.927, right? It isn't wrong, it's just basically multiplying by 3.14, the actual decimal for pi, not 180 or whatever the equivalent would be, right? All right, so this is the radian equivalent. Right. Sometimes that gets muddled. Right. Okay. If you have a situation naturally where you have something that isn't sine, cosine, or tangent, which are we have buttons for that. Right? If you had secant of theta, right, and it's equal to maybe a peculiar number, -4, right? Use an identity first. Right, so what is the reciprocal of secant? It's 1 over cosine. You just have to manipulate it a bit, right? Remember, you want to solve for theta, but you have to have it on the regular tier, not as a denominator. So we will multiply by cosine here, cancellation effect, and then do it here. And then you would have -4 cosine of the angle is equal to 1. Move the coefficient, divide by -4, and this is really what you have. Let me move this. Cosine of theta is equal to -1 over 4. Remember, the negative has to be carted up to the top, because if that is a radius, it can't be negative. All right. So 1 and 4 is not a special right triangle relationship, and I would be have a difficult time of trying to force it to be proportional. All right. So I'm going to use my calculator to get theta, in which case I'm going to go for the inverse cosine of -1 over 4. Okay. Just realize that there's going to be limitations, right, to what the calculator can do. If you type in -1 over 4, like so. This is still set in radian mode. You're going to get a decimal, 1.82, all right, which may be meaningless to you, all right, but just realize what that means, that the calculator has used 3.14 in place of pi, not 180, all right, so you could switch it to radian degrees, duplicate this by highlighting it, and then enter again, and it'll give you the degree angle, 104 approximately. Okay. All right, let's do a quadratic one. Suppose you had this to solve cosine squared of the angle plus 3 cosine of the angle, right, minus 1 equals 0. Right? A little alarm might go off in your head when you see something like this that is set equal to 0, to go from all the brainwashing, right, of having done so many problems from, quadratics. Oh, well, geez, maybe I should try to factor that, all right? I would go that route first. Let me add to this that the interval that is being asked for is from 0 to 2 pi again. More or less what is normal for cosine. This is something that behaves quadratically because it has a degree of 2 here. Right? So I'm going to try a couple of different things. All right. This is the order in which I would put forth the effort. Right? All right. When you have something that is, I'm putting this in quotation marks, quadratic, that is degree 2. All right. Try to factor first. Right. If that fails, then attempt, the quadratic formula. Right. You could use the quadratic formula 100% of the time. It will work 100% of the time, but it might be more trouble than it's worth because it does involve a lot. As an added thought to this, you might also employ U substitution. All right, remember, U substitution is just temporarily disguising what you are given so that you don't get bogged down with scary details. All right? In order to qualify for U substitution, there are a couple of conditions that you would want to meet. All right, you want something that is sort of trinomial-esque. I'm using the word, the suffix here, esque, because it's not quite a trinomial. Technically, it's not an algebraic equation, really. It's got trig stuff in it. All right, but it is something in 3 terms. All right, so trinomial-esque. All right, number 2. Let's see. The things that have degree exponents are the same bases. Right. I know this is kind of weird to think of this as a base, but it is, because here's an exponent of 2, so that makes this a base. This is the same type of base, it's cosine, so that qualifies. 3, the third term has to be a constant. right? It's just 1, so far so good, right? And then the last criteria here is that it doesn't have to be 2, it could be 4 here and 2 there. Or, you know, in theory, 6 here and then 3 there, all right? The degree of the first is double the degree of the second. This is degree 2, this is degree 1, so the degree of the first is double the degree of the second, so it's perfect for U substitution. All right, here's the advantage of doing that. And incidentally, if you don't like the letter U, you could use the letter X. All right. Usually it starts with X. I mean, that's where U substitution began in our lives. Anyhow, if we call this ugly thing temporarily X, all right, then that makes it 3X, you know? And in place of cosine, we'll have X squared here, all right? And then minus 1, and we'll lose my marker, all right? And this is equal to 0. Now, as I said, I'm gonna try to factor this first. Right? Because if I can factor it, then I could use the 0 product rule. If it fails, right, then I will use the quadratic formula. Being as it is, now a slightly less intimidating, truly trinomial expression here, x squared plus 3x minus 1. I might just be able to tinker with this, right? And figure out, well, there's normally a binomial here and a binomial here, and see if I can get it to work, right? Or I can use AC product pairs and factoring by grouping. It really doesn't require that because there's no coefficient up in the front to sort of make it more complicated. If it's x squared, then this would be, the first term here is x, and the second term here is x, right? What would make 1, though? It only has, it's not even a prime number 1. Right? It's neither prime nor composite, it is its own thing. It has one factor. 1 times 1 is the only thing that makes 1. Is that in any way in hell going to make 3 here? All right? It's not going to work. All right? Even if I added them, I'm going to get 2, which is short of 3. If I subtract them, I'm going to get 0, which is even worse. All right? This is something that, unfortunately, cannot be factored. All right, and there's a word for that. All right, it is prime, we would say. And prime candidates are what you would use a quadratic formula for. Anyhow, even if you're going, you might say, I wasted time using U substitution. No, it is not a waste of time because the quadratic formula, which we have to use now, looks like this, right? It's negative b plus or minus the square root of b squared minus 4ac, all sitting on top of what? 2a, right? I would still need to know the coefficients that would have been in front of x in theory, right? I'll reverse the substitution later, but for right now, just not to get bogged down, what was the coefficient here? Well, it technically would have been 1, all right? What is the coefficient here? It's 3. What's the constant here? Negative 1, technically. All right, so I would have to insert 1, 3, and negative 1 in the quadratic formula now, right? So be careful. I would use little parentheses when I'm substituting, just not to, to circumvent an issue with maybe the sign, right? Because there are negatives in the formula, all right? But when you get to something like a square, you don't want to just inadvertently square the digit and not the negative also, if it happens to work out that way. So in the case of b, right, this is a, b, and c respectively, right? According to the model, ax squared plus bx plus c, right? Model. I'm going to put 3 here and here simultaneously, and a 1 here, and a negative 1 here, and then a 1 there. I need the space. And let me do this. Okay. This is going to be you should always deal with the inner guts here, the radicand, otherwise known as the discriminant of this formula. Follow the order of operations, innermost parentheses first, well, it would be this you're looking at here. Square instead of multiply, because it's more important. So this is 9, all right? If you straighten out -4, well, -4 times 1 times -1, this is going to be +4, all right? Which means that this will reduce to x is equal to -3 plus or minus the square root of 13 over 2, right? Which is not a warm fuzzy answer, but it's correct. All right. To add issue to this, all right, we now have to reverse the substitution. Standing in place of x, this is really cosine of theta, right? So the cosine of theta is going to be two things simultaneously. Okay? Need the space. It is going to be -3 plus the square root of 13 over 2. All right, and then sitting next to it, -3 minus the square root of 13 over 2. Okay. And we are going to invoke, an inverse to get theta, right? Which means that in this instance, top here, theta is going to be the inverse cosine of this awful ratio, right? -3 plus the square root of 13 over 2, and that's not factorable 13, right? And in theory, the alternative would be this. Cosine of the inverse function, inverse cosine, and using this instead. -3 minus the square root of 13 over 2. Now here's where your calculator is unfortunately going to get you in trouble. All right. This is a bit of a nuisance, but let's type this first to illustrate the point. Clear. All right, and I'm going to, as I mentioned, I'm going to start with degree mode because all right, it's a little bit more intuitive, at least to myself. All right, the inverse cosine of this ratio, we have quite a lot here as a numerator, so I would isolate that in parentheses. All right. Be extra anal retentive when you're entering this. I'm putting a second parentheses to sort of encapsulate this. It might be overkill, but it's better safe than sorry, especially if you have to write something multiple times. I'm doing that, essentially. Right? The reason that I tend not to want to do it just very quickly is because a lot of times it makes the mistake of thinking that this 2 is just attached to here, not to there. So, -3, and I'm using that button here, minus, plus the square root of 13, and it looks like that to start with, divided by 2, close the parentheses. And it gives you a satisfying answer, 72.3 degrees, right? 72.4 maybe, all right? This is about, as it is not a special right triangle relationship, it's about 72.4 degrees, right? Which we could then convert to pi radians if necessary, right? Or just full-blown decimal equivalent. All right. I'll do it both ways. Sorry, I'm itchy. I gotta torture myself. I'm gonna put this in radians. Mode. And I'll show you what the decimal looks like. All right, here's the same thing, highlighted, duplicated, and you'll see that is the decimal equivalent, right? Using 3.14 as opposed to 180. So this is alternatively 1.26, something like that. Now watch what happens when you attempt to use this other algebraically correct solution. All right, I'm going to have to painstakingly duplicate what I wrote. I'll start with degrees again, just to keep that the way it should be, mode degrees. And now I have inverse cosine of -3, no, I'll just do the more attentive thing, -3 minus 13. Notice a couple of things for syntax to avoid. This is this button, negative, and this minus is the subtraction symbol. It doesn't make that distinction. It makes a distinction there when it possibly shouldn't. So 13, move on out, close that. This is as it would look. Divide by 2 again, close the parentheses, and now watch what happens. You go to math hell, and you go, error, all right? Why? Because there's a domain restriction, all right? The calculator, remember a couple of things here. Ordinary cosine, as what for a domain, right? The domain is from the 0 to 2 pi, right? Well, it could be into infinity, really, right? But it's usually, you know, the restricted domain is from 0 to 2 pi or something like that, right? If you're not starting at 0, then we go back, what was it, to pi over 2, I want to say, right? Remind myself here. Cosine. No, it's actually 0 to pi, sorry. Here's the drawing of cosine, right? Starting here, +1, -1. This is what cosine normally looks like, right? At pi over 2, pi, 3 pi over 2, and 2 pi, the usual interval here, right? We have this curve usually, right? But because we are using an inverse, right, we end up with a restricted domain. And a restricted domain, using integral notation, is from here to here, all right? Simultaneously, right? Which means that this is chopped off. And then the inverse, right, ends up looking something like this. It's hard to draw this, but a little bit above this would be pi over 2. If this is 1 here, you end up with a curve just back here a little bit. Something that looks like that instead. All right. Let me show you an old picture, because my illustration is kind of lacking here. Here's an old photograph, an illustration I give you. When we were deriving the inverse, right? All right, we basically had to shorten the interval of cosine, right? And it becomes an interval of 0 to pi, basically, right? And then switch the x and the y values so that the domain and the range switches, right? This, which is in red in this drawing, is the inverse cosine, which is why it's up here rather than down there, right? Anyhow, because of the initial domain restriction, right? That's why you're getting an error here, right? In spite of anything that's unique to the problem. There's a domain restriction in the software, all right? That's a situation for ordinary cosine. The inverse cosine, which is what we're using to find theta, right? The angle, right? Has this as its domain. This value, all right, let's just to prove a point, let's get the actual decimal number of this ratio. Clear out a lot. If I just got the calculator to calculate -3 plus the square root of 13 divided by 2. Not as part of an argument, just the value of that. See what you get. You get 0.3. That's just a regular ordinary number, right? This is the regular ordinary decimal, 0.3 something, right? That's something that would fit in here, right? Because it's under the magnitude of 1, right? If instead there is look, you have opposite signs causes subtraction, same signs cause amplification and addition, right? If I did almost the exact same thing, but I opted for, instead of adding, I subtract, there's going to be, ironically, an amplification effect, right? Look what you get as a value. -3, right? Which is beyond the domain of the inverse, right? So that's why there's an error message, right? So what we can do is just try to reason it through here. I erased it, unfortunately, I'll put it back now. Oh no, it's still here. All right. If this is the interval that they want us to give solutions, we're going to take this value, all right, and see what we can get. All right. All right. I'm going to draw a picture. All right. Let's see what we could get in here that fits into the regular interval of 2 pi. Here's our unit circle. Sloppily drawn. little backtracking here. If we started out with the cosine of theta is equal to this in blue here. And what is in blue here is really that decimal, which is really a positive 0.3 something, just not to have to write square root 13, whatever, right? What is that usually? This is an x value over an r value, right? X would have to be a positive, right? So where is x positive? Right? X would be positive in the first quadrant and in the fourth quadrant. Yeah. So in theory, it's a diagonal line. I don't know what the dimensions are because it's not a special right triangle, but it would have to be here, all right? 0.3, you know. Or alternatively, it would be in here. Right? It would still be a positive x dimension. Right? These are both positive x's. Right? So, because we can't use the calculator because of the software is having to take the domain restriction into account, right? We're going to try to finagle, what the other possibility is, right? Yeah. The visual aid, I think, is really helpful, right? Sorry, my drawing is not that great, but the idea of it. This is moving in a counterclockwise positive theta direction, all right? And in this instance, the quickest path to here is to go whatever this angle would be, all right, running in a negative theta direction. All right. So we figured that the angle is 72.4. Again, I hate that they've used the decimal here. All right, I think the angle is a little bit easier to understand. We want the value from this direction, but in order to figure out what this should be, we're going to backtrack from not 0, but from 360, which is the same location. So basically, what is 360 degrees minus 72.4, roughly? All right. It would be 287.6, I believe. Let me just verify. 360 minus 72.4. I did round mid-calculation, which is not always good idea, but 287.6. It's 72 degrees roughly this way, but to read it in the normal way, which is to read it ironically counterclockwise perhaps, this is what the other angle would be in this interval, all right? The calculator can only give you, for cosine, this one value, right? It only gives you basically quadrant 1 and quadrant 3s, right? Working in that range. All right, if you got the decimal equivalent here, right, this is radians, 1.26, right? What you would do is basically instead of 360 degrees, right, you would use 2 pi, right, which is 6.28 something, right, minus 1.26. So if you wanted the answer in radians, decimal radians, not pi radians, all right, it would be that, which is 5.2, something like that, 5.02 radians. Let's see, hypothetically, I'll use an exact pi. Here's 2 pi, 6.28, whatever it is, minus 1.26 approximately. It's about 5.2 decimal radians. Again, I don't want to corrupt your opinion. I think that, especially when you're drawing a picture to help you figure this out, degrees is more intuitive, right? Because that's what we start with, right? Even if it isn't the most, the best, you know, it's arbitrary and just cut something into 360 degrees, it's still familiar. Like in the argument, the analogy I always use is like temperature scale. As an American, you know, for better or for worse, we think of the number 20 as being cold, right, on a temperature scale because we grew up with the feeling, you know, which is why it's hard to get people to acclimate to, you know, Celsius scale. Right? The number gives you a feeling. Okay. All right. Let's see. I want to do one at least that works with factoring. So because that was kind of a hard problem because you end up having to use substitute and use the quadratic formula. Well, how about something that, you know, you will actually factor successfully? Okay. A problem like this. Getting very cold. Sorry. Solve two sine squared of theta minus 5 sine of theta plus 3 equals 0. All right. Again, this is the basic strategy. Do try factoring first, and especially if it's set equal to 0. You can take advantage of the zero product rule. Quadratic formula works 100% of the time, but as you can already tell, you know, it's kind of a nuisance for the use of radicals. So we're going to try to hope that this factors, right? In order to get it to factor, it might be a better course to use substitution somehow, right? I'll use x's in place of u since there isn't an x here to begin with. All right. This passes the qualification process. It's trinomial-esque, right? The degree, the bases are the same. They're both sines. All right. The third term is a constant. Coincidentally, it's 3. And the degree of the first thing is double to the degree of the second thing, which is just technically 1. So I'm just going to call this x, and therefore this is 2x squared plus 3. Right? Now, if I'm going to factor this is a good example of the factoring technique that is AC product pairs. And factoring by grouping simultaneously. Those two things often occur together. This is getting to be bad too. All right. Why use this? Because you have a coefficient up in the front that's not just 1. So this is your A, and this is your C. Right? Thing at the front here, thing at the back always. All right. This is the model, ax squared plus bx plus c, if you're wondering. A times c is a product of 6, and 6 has these as options. Either 1 times 6 makes 6, or 2 times 3 makes 6. Right? It just so happens that both of these potentially would make 5, right? But only one of them is really going to be the choice of choices. Right? Even when I was factoring myself, I chose poorly, you know? I don't know if you've ever seen Indiana Jones and The Last Crusade. There's a line in the movie, he chose poorly, right? And one of the Nazis basically melts, you know? Anyhow, or disintegrates in the story. Anyhow, it's actually these two, just to save time, right? Both of them would make 5 in theory, but only one of them is going to be the correct sign combination. This is going to be 2x and 3x combined to make that. This 3 is sitting here, and this 2x squared is sitting here. In order for these things to add, they both have to be negative. Right? Now, the advantage to using AC product pairs, although it would superficially seem to make things worse because now it's 4 terms as opposed to 3 terms, is that you only have to pay attention to 2 things at once, right? When you're factoring. Just factor these 2 things, and it's pretty easy because they have simultaneously a letter in common and a coefficient in common. So that is the thing outside parentheses. 2x times x is x squared, and minus 1 would produce itself. This thing doesn't have a letter in common, but it does have a number in common. And I would always start with the sign here, so negative 3. Negative 3 times x is what it is. And then minus 1 would produce a positive 3. This factors perfectly because what ends up happening is that the match can be written in the parentheses by itself. And then the thing that I personally refer to as the left outs can be in their own parentheses as well. So these are the match, write them once, x minus 1. And these things are the left outs. So it's 2x minus 3. Right? Meanwhile, this is still all equal to, and this was the whole point of it, 0, right? We're going to have to reverse the substitution because it's a sign function as opposed to a letter x, but we're ready to do that. Okay. So I need the space. I'm going to erase this. And I'll write it up here. All right. If this factored as x minus 1 and then 2x minus 3 equals 0. This x minus 1 is equal to 0 potentially according to the 0 product rule. And this 2x minus 3 by itself is potentially 0. Maybe manipulate it before substituting, right? You can get away with doing it either way, but it's up to you. Move 1 by adding. X is equal to 1, which is a stand-in for cosine. Cosine of theta equals 1. All right. In this case, you're going to move 3 by adding. You see that the old algebraic techniques will always come back, you know, use them forever. And in this case, you divide by 2. So standing in place of x here, cosine of theta in theory is 3 over 2. We're probably going to get in trouble again as we had before. But this is where we're working now. We have cosine is equal exactly to 1. And this is cosine is equal to 1.5 technically. All right. If we use an inverse function, right, we could establish what theta is, right? So inverse of 1, and you really don't need to calculate for that. You could draw a picture, and I'll show you in a moment. But you would do, in theory, the same thing here, right? The inverse of this ratio. Right? Now, this is an improper fraction, 3 over 2. It is really 1.5, right? Or you could say 1.5. For cosine, right? Or no, what am I saying? We're using sine, dopey, right? I'm sorry. I think my brain is freezing from being in the cold so long. Right. Sine, not cosine, where did that? Right. if you remember, and again I'll refer back to this diagram because it's easier than drawing a picture. Here is inverse cosine. Right? Ordinary cosine, right, when it is restricted, right, looks like this. It's back further rather than starting from zero. Right? Negative pi, so negative 90 degrees beyond here, this way. Right? To pi over 2. Negative pi over 2 to pi over 2. So negative 90 to 90. Right? The inverse switches domain and range, which is why this is labeled as the range, right? As if it was a y. And that's why you see the increments along the y-axis are in degrees, are in angle measurement. You know, the domain is negative 1 to 1, right? Now, this problem is a little different from the last one, right? Because in the last problem, the one that was involving cosine problem, we were looking we're still doing the same thing. For an angle, right? And we are really doing that in this case as well, but now this is sine. Right? So the range is be labeling the point here, but technically the ranges are a little different, right? Here's the range technically for sine versus here's the range for cosine, right? 0 to pi as opposed to negative pi over 2, right? All right. Anyhow, if you try this again, you're going to get in trouble, right? Because in both cases, the domain restriction is negative 1 to positive 1, right? Still, right? That is true for both of these. So watch what happens, you know. And I have my calculator set to degree mode still. This one is fine, but the inverse sine of 3 over 2, which you could kind of tell if you went so far as to convert it to a mixed number, 1.5 at least, it's above the magnitude, right, of 1 to 1. So here you see, if you attempt to do that, you get an error message, right? All right, so in this case, your theta is going to be, it should just be 90, I believe, right? Yeah, right. If you drew an old-fashioned sine curve, you could guess it even without the calculator. I know that this is range restricted, domain restricted, but here's ordinary cosine, right? It looks like this, right? And your value is actually 1, right? So where is sine equal to positive 1? At the location of pi over 2, which is just at the border of where it's restricted, right? Because in the restricted version of this, it goes negative 1. negative pi over 2, right, to positive pi over 2. Right? Where's positive 1 though? Specifically at that value, right? So let's enter that with your calculator. The inverse sine of just regular ordinary 1, 90 degrees. 90 degrees, otherwise known as pi over 2, right? That is right on the border, right? If you want to check, right, that this is still, everything is copacetic, right, draw a unit circle. Right. And remember that sine of theta is a y value over an r value. And since it happens to be positive 1, this is going to be right on an axis, it sounds like. All right, yeah, 90 degrees it would be, right? If this is positive 1, you know, where is y positive, right? Y would be positive above the horizontal axis. So it would be in technically quadrant 1 or quadrant 2 to start with. But it just so happens that since it happens to be 1 and not even a ratio as in some kind of a fraction, that means that this is the same value. That means that this is where the y is, right? Which means that there's only one answer in this case, all right? Okay, it is in between the quadrants. I'll make a note to myself about something. Let me do 2 or 3 more of these and I'll stop, I promise. Scratches. I remember seeing that. Okay. If an identity question comes up other than reciprocal identities, right, it would be a Pythagorean identity. So, suppose you had this. 3 cosine of theta plus 3 is equal to 2 sine squared of theta. What is interesting about this problem, and we want it in this interval again, from 0 to 2 pi, the usual interval. Right? This is interesting because, right, look at what is involved here. These are different trig functions. Right? So, what we would want to do is try to make them the same. Right? And in that case, we're going to employ an identity. Right? The kind of identity that has been discussed to this point is either reciprocal identities, right? Technically odd or even, or Pythagorean. All right, and since this is squared, that's the route we're going to go most likely. All right. Famously, right, sine squared of theta plus cosine squared of theta is equal to 1. Right? That's the Pythagorean identity. It's the Pythagorean theorem using trig functions. All right? If this were rearranged to solve for sine, that would imply that the cosine was scooted over. Right? So this would be equal to 1 minus cosine squared of theta. We want to go that route to substitute this so that it is exclusively the same trig function, not two different ones. Right? What that means is 3 cosine of theta plus 3 can be rewritten as equal to 2 times that expression, 1 minus the cosine squared of theta. We would have to do a little distributing algebraically, but it's nothing you can't handle. You know, just multiply by 2, multiply by 2. Right? So you end up with this, 3 cosine of theta plus 3 is equal to 2 minus 2 cosine squared of theta. All right, and now bring everything over to one side. Right? Being that this would be the lead term here because of the degree 2, right? And it is a negative, unfortunately. I would bring this over to the left side intentionally. All right? How so? Via opposite operations, and you would do it twice. All right? In this case, maybe do the 2 first because it is easy. Right? Opposite of adding 2 is subtracting 2. Cancel this, plop it under its buddy here. All right? Opposite of subtracting 2 is adding 2 cosine squared of theta. And it isn't a like term, so technically it would be not immediately underneath cosine, it would be adjacent to it. So plus 2 cosine squared of theta. Right? It would cancel here, everything would be 0 on this side, and maybe it's factorable. Maybe it's factorable, you have to check. Okay, to write this a little bit more cleanly, we end up with this. 2 cosine squared of theta plus 3, because that was there, cosine of theta, plus 1 is equal to 0 instead. This is indeed factorable, and what you would get is this. If you don't want to use substitution, you really don't have to, all right? But it's to your advantage sometimes. Right? So this is the way it's going to factor. You're going to end up with 2 cosine of theta plus 1. And in the other instance, cosine of theta plus something here, plus 1. Okay. I'm just going to verify by foiling here. This times this would be that squared with a 2 in front. 2 times that would be 2. 1 times that would be 1. They're both the same degree. They're like terms. You can get a 3. And then 1 times 1 is positive. Good. So that's the way that would factor. Right? If I brute force my way factoring rather than using substitution, you might get it faster, but it's really depends on you. You know how comfortable you feel. All right. Anyhow, this would now employ zero product rule, and what you would end up in this instance is that you get the cosine is equal to moving -1 over 2. Right? And in this case, you get cosine of theta is equal to -1. Again, draw a picture. You have a habit of drawing a picture. It helps, right? And look at what you have. You have special right triangle relationships How do I know? Because I see 1 and 2, right? And then this one is just a sad lonely 1 that's probably on an axis, right? If cosine is really an x value, and it's a negative, negative x would be on this side, right? So in theory, right, where is x negative? X could be negative in quadrant 2, right, or quadrant 3, technically. Right, so I'm going to start by drawing that. And a right triangle here. And maybe another one here. And this would be negative x here and here, right? If it just so happens that this is involving 1 and 2, right? The special right triangle relationships that I have to choose from are the 30, 60, 90, or the 45, 45, 90, right? Those that incorporate 1 and 2 would be the 30, 60, 90. So if it were oriented as a 30 here and a 90 here and a 60 here, then this would be the square root of 3, this would be 1, and that would be 2. Now it could be that orientation or it could be turned. All right, if it's 45, 45, 90, it's much easier because it's just 1, 1 and the square root of 2. All right. In this case, right, x is equal to 1, right? So if x is equal to 1, then these two things have to switch. And that means that you're really starting from 60. Right? If this is x is equal to negative 1 in here, sorry for the sloppiness, negative 1, then 30 would be here instead. Right? Because 30 and 1 are opposite of each other, not adjacent. Square root of 3 is adjacent to 30. Right? So this is really a 60-degree angle from the more or less the standard position, not technically, but you know what I mean. It's not riding on the axis here. Okay, so if you start from 0 and you read to the terminal here, right? In order to get that, you would take 180 and subtract 60 in this case. Right. So 180 minus 60 is what? 120 degrees. All right. 120, since we're looking for theta, is 120 times pi over 180, cross out the zeros. Divide each of these things by 6, that's a 2. This is 3, 2/3, all right? One theta that is possible is the 120, is really 2/3 pi. If we read from 0 to this terminal side here, then that would be 180 plus an additional 60, because this has to be the same angle, right? Which would be, what, 240 it looks like? Yeah, 240. Right? 240 times pi over 180, cross out the zeros, divide by 6. Right? 24 divided by 6 is 4. Right? 18 divided by 6 is 3. So a second theta would be 4 pi over 3. I'm getting raspy, sorry. So do these things fit in the one revolution? Yes. All right. But there is the other possibility. There's that one. Right? Where is that one? That one is another example of where you're not given a fraction. right? You're given just a single number, -1, which means that r and x are in fact the same dimension. It's right there, right, in between these two. Right? So if you read again from 0 to this terminal side, that is exactly 180 degrees. So a third theta in this interval, all right, is pi itself. Right? You get 3 angles in that case. All right. 2 pi over 3, 4 pi over 3, and just pi itself. I'm debating this other example, I'm sorry. Times it 2 and ticking good. Okay. All right. Let me do another weird one. Suppose you had this situation. The cosine of, we're just going to use the variable x here in the argument, and this is equal to 1/2. Right? This is another situation where you might try to get it to be something like 1-to-1. The only downside to this, I hate that they use the letter x here, but if it comes up, you can finagle, right? Now, if you pay attention to just this side, right? The way that the example was written was that they have the interval notation rather than sort of the inequality, compound inequality, but this means the same thing. You're bound in one revolution here, right? Let's see. This is a special right triangle relationship. And if we can envision this as just being the normal situation, cosine of theta is equal to the ratio of 1/2. You could figure out what the angle would be under those normal situations. In a case like this, right, this is the special right triangle of, if it involves 1 and 2, what would normally be written like this, right? The 30, 60, 90 triangle. If it were oriented in standard position, then the angle that is running between here and sort of this side, I should say, is a 30-degree angle. Right. And this would be 60 here. Right. When you have a cosine though, as opposed to a sine. Let's see what we have. This is implying that this is x, right? And that is the r, right? So cosine of what angle? Let's see. What would be adjacent to 1 would be 60, not 30. You'd have an orientation like this instead. Here, 1, x equals 1, as opposed to this is y equals. Square root 3 would be here, and that would be 2. So we're talking about a theta that is, to get started, 60 degrees. Why am I concerned with that at all? Because what I'm trying to imagine is this kind of combined with this, right? This information. Right. I just might opt instead for pi radians as opposed to 60. All right. 60 degrees is pi over 3, right? Okay, I'm not quite doing 1-to-1 here, but I am trying to combine some thoughts, all right? Normally, we would just simply refer to this as pi, as theta, an angle, but instead we have an expression that is being used in that place. It is nonetheless equal to this relationship. So, if theta causes basically this situation, then this thing that is standing in place of it, which is 2x, is still causing that situation, right? But it would be equal to the angle that is 60 degrees, right? Or instead of saying 60, it would be pi over 3. Pi over 3 is equal to 2x. That is a sort of a teeny tiny little equation that I could finagle from considering the usual situation. Right? In order to solve for x in this case, I would have to manipulate just a little bit. Right? So I'm going to divide by 2 here to cancel, and then technically divide by 2 here. Right? I'll just use the colon symbol. Right? The effect is that you have pi sitting on top of 3 times 2, right? Which means that x is actually equal to pi over 6. Right? Now there may be more than one solution to this, right, in the interval that is quoted to you. Right? So maybe draw a picture to help. I understand it. So I'm going to draw again a unit circle and a situation like this. Right. And we're using this as x. Right. So what is that incidentally? That's 30 degrees. Right. So in the interval of 0 to 2 pi, also known as 360. All right, let's see where we would have, in theory, a positive x value. Right, that creates that angle. Right. Let's see. Well, I'm sorry, I'm burping. If I'm going to draw a diagonal line here, I have this angle that is, it's really 30 degrees. I know that we derived this from 60, but that's just based upon this ratio. All right. If this is 30 here, and that's a positive x, quadrant 1 and quadrant 4 again. So in theory, I have 30 this way as well. In this direction, it's positive 30, right? And in this direction, it's negative 30, right? In the style of pi radians, it would be positive pi over 6, and in this direction, negative pi over 6, right? So my one theta that I have established for sure is pi over 6. Right. It's calling it x though instead of theta, sorry. All right, what is the other possibility here in this interval? All right. Reading from here to this terminal side in the more or less normal way, right, would be subtracting from 360. So 360 minus 30 degrees is 330 degrees. Right? So my second possible x, right, is equal to what? Well, if it's 330 times pi over 180, I'm going to use a conversion factor and divide by 3's, is it? Let's see. Very cold. 3 goes into this 11 times, 3 goes into this 6 times. 11 pi over 6. Is the other possibility. All right. I'm trying to think if you can get away with doing anything else here. Let me see something. Okay. I'm thinking it might be possible to be 5 pi over 6 and 7 pi over 6 as well, but it's not really super important. We'll go on. Here's the last thing. This is an example of one of the word problems that you end up having to solve for a length and also an angle. What was described in this example, this would have been 18 in our textbook, right, is the London Eye, the Ferris wheel. That is, according to the description here, secured to the ground like so. What is asked of you is to calculate based upon these dimensions. If the height of this is 69.5 meters, right, and the distance from that point directly under the center, right, to where there's a stake or something. I hope it's not just one literal piece of wood. The distance from here to here is 23 meters. Right? What would be the angle in here? And what would be the radius, essentially? Right? This length that is a question, right? And this angle that is in question. Right? Well, consider what dimensions you're given in relation to this angle here. If you have the choices of sine, cosine, or tangent, right, based upon the SOHCAHTOA version of these ratios, opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. Marker's dying here. Which does this most closely resemble of those three choices? You're given a dimension opposite, and you're given a dimension that is adjacent. So tangents would be the prime candidate here. In which case, you would insert the dimension 69.5 meters, right, and 23 in here, and then use the inverse function of 69.5 over 23 to calculate the angle. Right? In that case, you get an angle that is approximately 71.669, almost 72 degrees. Something like that. Right? As for the dimension here, you could just use plain ordinary Pythagorean theorem. Right? Just call it x squared plus y squared equals r squared. And then you would insert 69.5, 23, and your length here, let's call it r, is equal to this. 69.5 squared plus 23 squared, and you'll have to round it because of the radical here. So you would get something like 73.2 meters. Okay? Let me leave it at that. About 3 hours here and I'm freezing. So we're gonna call it quits today. All right, I'm gonna look at the homework to see what is included and what's not. Again, you should not be responsible for identities, double angle, half angle, or some differences of product of sum, because we haven't discussed that yet. All right, it's just out of sync with the textbook. So right now, what you can expect is for homework, you would do section 9.5 practice, all right, in My Open Math, and that's it. Okay, due by, say today's Tuesday next week. Okay. And that's that. Okay. Thank you for sticking with me for 3 hours. I'm gonna go warm up now. All right, be careful out there.